Today I'm going to present DeepErr, an automatic root cause analysis of system call failures, which is a study that Michael Way and I conducted. Let's start with an example. Here is a simple FCNTL system call that fails with E-again error code. Tools like strace can find the failing system call, but cannot tell us why it happened. Which of the dozens of conditions in the kernel trigger this error? The challenge is threefold. First, this is kernel code, which most people are unfamiliar with. Second, it runs in privileged code mode. And third, we often do not have a similar successful execution to compare against. But handling errors of other software components is often manageable. Why is this so hard in the case of kernel errors? Looking at real Stack Overflow reports, we find these errors are encountered both during development and after deployment, and it's certainly harder to analyze deployed systems. The fundamental issue is error code overloading. The e-inval error code maps to 47 different failure conditions in mmap alone. Documentation makes it worse with vague descriptions like invalid argument. But which argument? We found serious documentation errors too. At the 2024 Linux Storage Summit, a kernel developer articulated the community's frustration. POSIX error codes are simply too generic. Many solutions have been attempted. Kernel modifications from Google, Red Hat, and Meta were all rejected. They broke internal kernel ABIs and required modifying thousands of return sites. Even if implemented, they wouldn't identify the exact failing predicate. Academic solutions are insufficient too. Comparative analysis needs successful reference executions, impossible for the infinite state space of system calls, which also depend on the operating system state from previous calls. Delta debugging assumes deterministic failures, as it tries to replay the failing flow with small variations repeatedly. Besides the extensive time this process takes, many system call failures involve timing or external resources. Execution slicing gives you thousands of instructions without identifying the specific cause. Practical debugging tools are helpful but limited. General tracing solutions like ftrace and eBPF, along with reverse debugging, require manual analysis and complex setups. RedSnoop is the only tool explicitly targeting our scenario, automatically finding system call failure causes, but it requires guessing where to trace, which is far from trivial. It only identifies the error returning function, leaving the user to find the actual function and predicate that triggered the failing, which might be completely different. Our goal is to simplify understanding of system call failures by identifying the exact predicate and call stack on the time of the failure. With these informations, developers can leverage code comments and commit logs to understand the failure cause. Our approach consists of three steps: recording a branch trace, simulating the failure using the symbolic execution engine, and backtracking to reverse predicates until we identify the potential successful execution resulting from reversed predicate. Let's explore how we achieve this. We start by recording a trace. DeepErr can use one of two tracing mechanisms, each with distinct trade-offs. Hardware tracing uses Intel processor trace, a CPU feature that traces all taken branches. When a failure occurs, we capture a snapshot of this branch trace. While apparently simple, hardware tracing has significant limitations. It's not always available, the trace buffer is limited, and most critically, it only traces branches, not predicated instructions like conditional moves. Since these instructions often map to the failing predicate in the source code, this limitation is impactful. Our second mechanism is a novel software tracing approach using Linux kernel probe points to instrument the code. We trace branches like Intel PT, but also record function return values, predicated instructions, and certain arithmetic operations compilers often use to evaluate predicates. While software tracing provides richer information, it requires reinvoking the failure multiple times. First to confirm reproduction, then to identify executing functions, and finally to set probe points in these functions. This causes significant overheads. These approaches are complementary. Hardware tracing is more suitable for production systems, while software tracing is better for development. After tracing is complete, we replay the trace using a symbolic execution engine. This is done for two purposes. In the case of hardware tracing, we use it to identify which function first returned the error code, which we still do not know, as we could not track return values. The second is to collect states that we would use in the next backtracking stage to find where executions went wrong. We follow the actual execution, starting from a fully symbolic initial state and handling divergences. In some cases, we can handle those gracefully by adding constraints during indirect branches. In others, not as much, which might impact correctness. Once we've identified the error originating function, we've established our starting point for the backtracking phase, which we will find the actual root cause. Finally, we move to backtracking, the process of identifying which predicate actually caused the failure. During simulation, we saved alternate states at each fork point where the execution could have taken a different path. We now process these saved states in reverse order, starting from the end of the trace and working backwards. For each fork point, we explore what would have happened if the execution had taken the alternative branch. The key question we are answering is, could negating this predicate have led to a successful execution? We use symbolic execution to explore each alternative path to completion. In Linux, success means returning either a non-negative value or a negative value outside of the error code range. When we find the predicate where taking the opposite branch would have resulted in successful execution, we've identified our root cause. That predicate becomes our answer, and the backtracking process terminates. Implementation required extending ANGR to handle privileged kernel instructions and simulating exceptions that can be the root cause in certain cases, along with many other corner cases. We discovered and fixed two kernel bugs along the way as well. The key challenge with symbolic execution is state explosion. We prevent this by stopping simulation as error returns, skipping Collie simulation during backtracking, and focusing on just the error returning function and its Collies. Our limitations include race conditions, non-deterministic failures, and compiler-optimized predicates that we do not handle. We evaluated DeepErr on 100 Linux test project tests covering 20 different system calls. Our results show DeepErr identified the exact failing predicate in 90% of the cases. Even when we couldn't identify the exact predicate, we found the correct function in over 95% of the time. For comparison, we also evaluated RedSnoop, a tool that traces function return values during system call failures. RedSnoop requires you to specify which kernel subsystem to trace. Although we directed it to monitor the kernel directory based on the error type, it only succeeded in 6% of the cases due to various limitations caused by the need of setting extensive number of probe points. Even when succeeding, RedSnoop, as we mentioned before, only finds which function returns the failure code. The case where DeepErr failed had various technical causes. 4 failures involved predicates compiled into conditional move instructions, and four others were optimized by the compiler into subtract and borrow arithmetic instructions which hardware tracing cannot trace. Some inline functions couldn't be traced due to technical kernel restrictions. Despite these limitations, we successfully diagnosed all five real stack exchange questions we tested. Performance matters for two reasons. Setting probe points for software tracing is slow, and symbolic execution is notoriously expensive. These figures show recording and analysis as cumulative distribution functions. What percentage of test recording and analysis completed within a given time? For recording on the left, software tracing takes over 80 seconds due to runtime patching that is required for setting probe points. Hardware tracing adds only 10 to 15 seconds, mostly from dumping the trace buffer to disk. Analysis time on the right shows an interesting reversal. Software tracing completes faster because it knows which function returned the error. Overall, we consider these overheads to be tolerable, especially since analysis runs offline on a different machine. DeepErr demonstrates that automatic root causing of system call failures is practical. We've shown two key innovations: probe-based software tracing that capture predicated instructions, not tracked by hardware, and symbolic execution that generates successful paths without reference execution, solving comparative and debugging a fundamental limitation. We achieve over 90% accuracy identifying root causes in real kernel code. Our implementation is open source on GitHub. We believe that these techniques can be used for additional use cases and hope to see them being adapted. Thank you.